Okay, welcome back. I want to clarify a few things about the assignments. The assignment numbers don't really mean very much. So assignment 1 will be basically on the algebraic graph theory. Assignment 2 will be on continuous quantum walks or analog quantum walks, and assignment 3 will be on the quantum homomorphisms. And your issue is, as I said before, you want to do hand in something like 50 correct solutions. Now, my problem is if I leave things as they are, then at the end of the course, you'll still be working on the first assignment and not looking at the current assignment. Now, if you look at the questions, there's in some sense in line with the order of doing things in a course. So what's going to happen is at certain times I'm going to say, well, you've got 2 weeks to hand in solutions to these questions, and after that, we won't accept them. And so you'll just have to move on. There's going to be plenty of questions. Okay, and so my only concern is to say that you do a good number of assignment questions correctly, and that they're spread out over the course. So, any questions about that? Okay. And the comment about doing it regularly is, well, I've always used this system, and if you're in the habit of leaving everything to the last minute and then try and do it, you'll discover it doesn't work very well. So that's the anyway. That's enough of that. So it's untangled. So I want to talk about orbits of permutation groups. Now, okay, let's just go on with that. So we have this statement here that I've got a group acting as a group of permutations of a set V. Okay, so I'm thinking of a group acting as a group of permutations of a vertex set of a graph. Now, the term permutation group, well, strictly speaking, it just means a subgroup of the symmetric group on some set, in this case V. Okay, but you'll also see he talks about actions and representations. So if somebody says there's an action, what they're saying there's a homomorphism from your group to something else. And so an action of a group on a set will be a homomorphism from the group into the symmetric group on that set. Okay. So when I was talking about the Peterson graph last time, I said I could view the symmetric group on 5 letters as acting on the 10 vertices of the Peterson graph. Okay. So in other words, there's a homomorphism, in this case a one-to-one map, that sends a symmetric group on 5 letters into the symmetric group on 10 letters. And so action is another word for homomorphism. You don't need to worry about too much anyway, but so let's explain. So if you talk about a group acting on a set, it's a slightly more complicated situation than just saying a group of permutations, but we won't need to worry too much about that. So the group acts on the set as permutations, then it partitions the set into, well, we'll see equivalence classes, and these equivalence classes are what we call orbits. So a lot of the time in mathematics, when you want a partition of some set, it's often best if you can get it as an equivalence classes. So we're going to say 2 elements of the underlying set are G equivalent if there's an element little g in big G that sends U to V. So if you can get if you can move U to V using an element little g of G, then we'll say that those 2 elements are G equivalent, where G is the group. Okay, now the point is, so we're going to note this in the obvious way, just use this as the equivalence symbol, then each vertex is equivalent to itself because the identity maps an element to itself. If U is equivalent to V, then V is equivalent to U, because if G maps U to V, then G inverse maps V to U. And so we're using the system of identity, the system of inverses. And finally, if U and V are equivalent and V and W are equivalent, then U and W are equivalent, because let's do this, if these are equivalent by some element G and this is equivalent by some element H, then, well, applying G and then H maps U to W. Okay, and so there we're using this, or the fact that the group's operation's closed. So we have the point is that this relation that we've just defined is an equivalence relation. And so you can partition the set V into equivalence classes. any two things in the same class, one vertex there can be mapped to any other vertex there. If they're in different classes, there's no permutation that takes one to the other. Just to take a simple example. So here's X, V is 1, 2, 3, 4. Now, any automorphism graph maps a vertex of degree K to a vertex of degree K, because it maps the set of neighbors of the vertex to the set of neighbors of the image. So since there's only one vertex of degree 3, any automorphism graph must fix the vertex 1. Okay, and so 1 by itself is an orbit. Okay, now on the other hand, if there's 6 automorphisms that permute the elements 2, 3, 4. If you swap 2 and 3, 2 to 3 and 3 to 2, that permutation, and fix 1 and 4, that permutation is not a morphism graph. And so you discover that there's exactly 2 orbits. Now, if you actually given the generators for a permutation group, finding the orbits is not a difficult problem. And so anyway, this example will suffice. Have any questions about that at this point? Okay. So we have a partition into orbits. And so when people are trying to study permutation groups like on sets, it's very natural to try and break things up and look at things orbit by orbit. Now, if there's only one orbit, I say this, we say that the group is transitive if it has just one orbit on the underlying set. So there's several uses of the word transitive in mathematics, and this is a different one. So the group is transitive if given each pair of points U and V, there's an automorphism that maps U to V. There might be more than one, but there's at least one. Okay, and so a transitive group is a group that has exactly one orbit. And I don't think I wrote it down, but a graph is transitive if its automorphism group is transitive on its vertices. Now, generally when we talk about orbits, we talk about orbits of groups. Occasionally we might slip up and talk about the orbits of an element, but in that case we really mean the orbits of the cyclic group generated by the element. Okay, so you can think of orbits as coming from groups, and now the
sorry, this definition of transitive, it depends on the action, right? I mean, if the same group G acts on another set, this
yes,
could be...
yes, you're right. And so, so for example, the symmetric group on 5 letters, if you act on the set 0 through 4 alternatively, in fact, it maps any pair of distinct points to any order pair of distinct points. So the jargon is that it acts 2 transitively. But when you look at the action on the vertices of the Pearson graph, the unordered pairs from 0 through 5, it is now transitive, but it is no longer 2 transitive. Because you can't map an overlapping pair of pairs to a disjoint pair of pairs. So it depends, yes, so you're right, the definition of transitiveness depends on the action. Now, we will not normally be in a situation, it'll be a bit unusual for us to be in a situation where we have one group with more than one action. It does happen, and I can't prevent it, but so generally speaking, I'll try and talk about permutation groups, and then I don't need to discuss the action. Does that help?
Yeah, thanks.
Yeah. Now the next thing is the point about using permutations, or considering the permutations you get and properties of those permutations, is it gives you, well, counting information or combinatorial information about the original group. So you can get a lot of information about your group by looking at the permutation representations. Now, the first step is quite important. We define a subgroup, what's going to be a subgroup G, the elements in the group G that map the vertex I to itself. Now, this is called the stabilizer of ING. Now it's clearly a subgroup, contains the identity, and if G fixes I, then G inverse fixes I, and if G and H both fixes I, so does their product. That should be an ID, not a G for somebody. There you are, there's a correct definition of stabilizer now. So it's a subgroup of G. Now, so if you have, it's best to think of this orbit by orbit. So if you have an orbit, each point in that orbit corresponds to a subgroup. And the actual correct statement is, well, the actual thing is, in a sense, the points of the orbit correspond to point stabilizers. Now, corresponds a vague word, and I annoy my students often by saying, well, if you people write things up and say this corresponds to this, and it's not at all clear what corresponds means. So what I mean is there's going to be a bijection from the points of the orbit to the point stabilizer. Well, to things later to the point stabilizer. In fact, what we need are cosets of the point stabilizer, and so that's what I want to get to next. So I defined the stabilizer, which consists of the elements in G that map I to itself. That's stabilizer I. We can also consider a kind of a generalization. This is not particularly standard, but we only need it for 1 or 2 slides, so it's not going to matter much. So we assume we've got an omega is an orbit of the group. We pick a point I in omega, and we define, and we're at the second point J, in fact, I'm just going to define G, I, arrows J to be the elements in G that map in the group G that map I to J. Now, this is not standard notation, but I'm only using it for 1 or 2 slides, so it's not a problem. Now, my claim is that this is a coset of G sub I. In fact, if you want to map I to J, you can pick any element in the stabilizer, which maps I to itself, and then pick a permutation which maps I to J. And every permutation maps I to J can be expressed in that form. That's since this is not a group 3 course, I'm not going to set it as an exercise, but every element that maps I to J can be expressed first, broken up in a number of ways. And the way I'm breaking up, I'm going to say, well, I'm going to have an element of G which fixes I, followed by an element of G which maps I to J. And so that set of elements will be is what I'm calling G sub I, comma J, and it's a coset of the stabilizer. And so these cosets, of course, the cosets of a subgroup partition the group. Okay, so and this leads to the orbit stabilizer relation, which is what I was working up to. If omega is an orbit of G and I is in omega, then the size of the orbit is equal to the index of the stabilizer, the number of cosets of G sub I and J. Okay, and maybe I should make that an exercise. This is, well, actually, I can't do that because this is written out in that book with Royal. But I'll take it as given. So this is the orbit stabilizer relation. And this is very important because when you're trying to determine the automorphism group of a graph, it's often not too hard to find a large bunch of automorphisms. Then you want to show there aren't any more. And so to give my common example, if I take the, Pearson graph, now so any automorphism of the Pearson graph moves the vertices around, moves the edges around. What I'm concerned about will be, I think I'll rather use a different color. Indulge me. So I just picked out a path of length 3. Now, the point about this path of length 3 is, well, these two, so let's take this to be the first vertex, then these two vertices are at distance 2. They can't be adjacent because there's no triangles. And this vertex can't be adjacent to this because there's no 4 cycles in the Pearson graph. The curve is 5. So this is the technical term. This would be an induced. So we have this path, and the distance in the path is the distance between vertices, is the distance in the graph. So in the exercise, I talk about geodetic subgraphs, and this is an example. Now, the point I want to make is that any automorphism of the Pearson graph must permute the paths of length 3. It must map a path of length 3 to a path of length 3.
Chris?
Yes?
We can't see which edges you're indicating.
I'm not indicating any edges at the moment.
Oh, okay.
Sorry.
You said this
So
edge
I'm
and
just
those
saying,
two edges.
I gave you an example of a path of length 3.
Okay.
I'll be annotating a diagram more in a minute. And what I'm claiming is that any automorphism graph must map a path of length 3 to a path of length 3.
Okay. And also your Pearson graph's missing an edge on the right side.
Oh, thank you. It's not going to. Yeah. Okay. Let's get it right. Okay. Now, so my question now is, how many paths of length 3 are there? Well, it's not too hard. You're going to construct a path of length 3. You've got to pick your first vertex. Let's call it, I'm going to start with call it 0. I'll stick to red. Whoops, right on here. So pick a first vertex, call it 0. Now we're trying to construct a path of length 3. Well, first thing you do is you go to a neighbor of 0. I'll just call this 1. Now there are 3 choices there. Now I should probably write down, I have 10 choices for my first vertex and 3 choices for the next vertex. Now the Pearson graph is a cubic graph. Each vertex has valency 3. This vertex has got 3 neighbors, one of which we've already seen. So there are 2 more. If I pick one of those neighbors and call it 2, then I get a path of length 2, and I have 2 choices for that. So 10 choices for this, 2 choices for this. I probably should choose a different numbering scheme. Now, the next step, and you would need to sit down and do a calculation, is to go from path length 3 to path length, length 2 to path length 3. You again have 2 choices. So that means in total. Now, as I said, there's some calculations. I'm not claiming this is immediate from the drawing, but you don't need to think about it very long. So in total, you get 10 by 3 by 4. It's 120 paths of length 3. Okay, now I claim 2 things. The second one is actually, I may even make an exercise, is any automorphism in the graph which fixes a path of length 3 must actually fix each vertex in the graph. The first step is to see that if you have a path of length 3, there's a unique vertex which you can add to turn it into a 5 cycle. Okay, and then you can, and from that, it's fairly easy to argue that if you fix the 4 vertices in a path of length 3, you must also fix all the other vertices. So I now have my automorphism group acting on the 120 paths of length 3, and the order of the stabilizer is 1. And so by the stabilizer theorem, that means the order of G is at most 120. Okay, and so I have an up bound on the order of the automorphism group. And then you fiddle around a little bit to construct enough so you can actually then, it's not too hard given that information to find a set of elements which generates a group of order 120. But the real point of this is simply that so the idea is that you pick some substructure which is pushed around by the group. And then you argue that things which fix that substructure, you know what they are, you know their size because you know a stabilizer, and the index of stabilizer gives you the order of the group. So it's a very useful tool in working with properties of graphs. Are there any questions at this point? So the point of this example is just that the orbit stabilizer relation is fundamental. You get to use it in many places. That's all I want to say about orbits for now. And so I need to go on to the upper level to what we call orbitals. And again, this is discussed in the algebraic graph theory with Gordon. And so the, well, this is related to what I was just saying. If I have a group of permutations on V, it also gives rise to a permutation of the set of K subsets of V. And for example, also on the ordered K tuples of elements of V. So the action of G on V gives rise to a number of other actions. Okay, and so in this case, since you're just acting on a set, it gives rise to, well, like K subsets of a set or ordered K tuples of a set. Okay, and so what I want to focus on now is the action on ordered pairs. Now, so here I'm acting on ordered pairs. Okay, and the assumption is that if I have a group element G, it maps the order pair U, V to UG, VG. So you just apply G to each coordinate. Okay. Now there's a definition coming. These things, the orbit of G on this set D cross V is called an orbital. Okay. So now the okay, this is an example which I've referred to before. If you take the permutation group to be Sim7 acting on the 3 element subsets of 0 through 6, so there are 35 such elements. Okay, and so the action of Sim7 on the set of size 7 gives rise to a homomorphism from Sim7 into the symmetric group on 35 things. That's an injective homomorphism, so you can view, in a sense, you can say that Sim5 is a subgroup, well, actually it's a subgroup in many ways of the symmetric group of 35 elements. So we have this set of 35 triples, and it's a good question to think about what are the orbitals in this case. Now, I'm largely leaving this as an exercise, but the point is that certainly if I have 2 triples which meet in one element, and then I apply an element of Sim7, the image of those 2 triples will still meet in exactly one element. So I'm going to have triples that meet in, or triples that are equal as one, okay? Triples that meet in 2 elements, triples that meet in 1 element, and triples that meet in none. And so that would give me at least 4 orbitals. Okay, so in this case, it's easy to see there are at least 4 orbitals. And the problem is, the question is, are there any more? And if there are more, then one of these orbitals would split into 2 subsets. Now, in fact, because you're working with a symmetric group, it's pretty easy to convince yourself that if you have 2 triples that meet in 2 elements, then their image under the symmetric group also intersects in exactly 2 elements. And if you have 2 pairs, each of which meet in exactly 2 elements, there's now the symmetric group taking the first pair to the second. Okay, so in this case, there are exactly 4 orbitals. Okay, things that intersect in 0, 1, 2, or 3. Now, intersecting in 3 is essentially the equality relation. Okay, and so the orbital consists of pairs alpha comma alpha, where alpha is a triple. And so, so just 2 copies of the same thing. So, and so that orbital, its size will be the number of, just the number of triples. You've got 35 triples of that form. Okay, but the interesting thing is that the other orbitals give you a graph. You just take the, now here's, to define arcs. No, let me define it now. So, an arc in X is an ordered pair of adjacent vertices. So sometimes people will refer to these things as oriented edges. I'm not too fond of that because I'm not sure how you give a mathematical definition of orient. The easiest thing is to talk about an arc. So if U is adjacent to V in a graph, actually I don't want, if U is adjacent to V, then I have 2 arcs, U comma V and V comma U. Now, if you have a graph which is transitive, sometimes you'd like a bit more symmetry. And so the obvious thing is to worry about the group being transitive on edges. But it's experimental fact that you're much better off to think about the action on the arcs rather than the edges. Now, it's not obvious in advance this is true, but just with the hindsight experience, it's better to work with arcs rather than edges. Okay, your life is easier. So to find an arc, okay, nor pair of adjacent vertices. Now, I can view each orbital as a collection of arcs. It's a collection of ordered pairs. Okay, and so each orbital is giving me a directed graph. Okay, I've got the underlying set and I've got arcs joining vertices, so I get a directed graph. So each orbital is a directed graph. Okay, and so the orbitals partition the arcs of the complete graph into subgraphs. Now, each of those subgraphs is vertex transitive because we started with things being vertex transitive, but they're also arc transitive because each orbital is an orbit of arcs. And so you've you've constructed a collection of arc transitive graphs from your from the group. Now, of course, generally speaking, we'd rather work with graphs than directed graphs. And so now the question is, when is an orbital giving me a graph rather than graph rather than a directed graph? Actually, I don't need to go into that right now. And so this is sort of summarizing what I said, that we always get the so-called diagonal orbital for free. Okay, so omega is an orbit, the diagonal is an orbital. Okay, and the orbitals are directed graphs, and that directed graph is vertex and arc transitive. Now, this is where it's going to get. Yeah, you'll love this. So, so the point is that by having a group acting transitively on a set, we get a partition of the ordered pairs of elements of the set into orbitals. Okay, each of which is a directed graph. Now, we can actually do things a little more generally. There's no particular reason to assume that G is acting transitively. We still get orbits, so we'll still get the group is acting on the set V, and it still shuffles the ordered pairs of elements of V around. Okay, and so each of those things is an orbital, and you can view that as giving me the arcs of a directed graph. Now, if the group is transitive, then the vertices of that directed graph are the vertices of the underlying set we're acting on. If the group is not transitive, some of those orbitals will have fewer vertices than that. I'll come back to that in a minute. But let's, what I'm essentially doing here is saying, well, if I have a graph acting on a set, I can partition the arcs into orbitals. Okay, that's in some sense a set theory combinatorial definition. I now want to write down in terms of matrices. Okay, so the point is that if I have these orbitals, then each thing is a directed graph, and so each thing has an adjacency matrix. Okay, so I'm denoting them by BI, the adjacency matrix. These matrices need not be symmetric. Okay, now the comments I want to make is that if the I and J are different, then the matrices BI, the Sher product of the matrices BI and BJ is 0. That just says the distinct orbitals don't have any arcs in common because they're orbits and orbits partition. So that's not too bad. Now, every arc, every ordered pair is in some orbital, so the sum of those matrices is 0-1 matrix. Okay, so you've got a collection of 0-1 matrices. The distinct matrices have Sher product 0. They sum to the identity. Now, actually, this one is an exercise, but I claim that if the transpose of BI must be one of those matrices. Okay, and the final thing, and so let me mark that. I probably should actually set that as an exercise. The final thing is that if you take an ordered pair x comma x and apply a group element to it, you get an ordered pair y comma y. So you map points on the diagonal to points on the diagonal. So the diagonal is a union of orbitals, or a union of orbits, depending how you want to think about it. Okay, and so the identity is a sum. So the identity is always given as a sum of matrices from the set B0 through BD. Okay, and so we have this collection of properties. Okay, and this is in a certain sense, a matrix 2 description of what's going on with the orbitals. On the other hand, you may have some graph where these properties hold and no automorphisms to play with. And yeah, the last one is again, where's my red? No. I did put in the for all I and j, the product matrix product BIBJ is a linear combination of things from B0 through BJ. Okay, so you have these 5 properties. Okay, and the matrices corresponding to the orbitals of any group acting on the Bezier graph satisfy these conditions. There are other examples, but for the moment, automorphism groups will do for us. Okay, now there's certain things you can say. If the original group is transitive, then I is one of the matrices in this basis. Okay, so oops, done it again. And I think I probably said that if the so the matrices B0 through BD generate a matrix algebra, and by virtue of this last fact, it's an algebra of dimension D plus an algebra of dimension D plus 1. Okay, because these guys form a basis. So they form an algebra of dimension D plus 1. It's closed under Schur multiplication because of this. So the point is that the set consisting of the 0 matrix and the matrices B0 through BD is closed under Schur multiplication. And therefore the algebra they generate is closed under Schur multiplication. So it's closed under Schur multiplication. It's closed under matrix multiplication. It contains the identity, which is the identity for matrix multiplication, and it contains J, which is the identity for Schur multiplication. So there's a lot of structure here. And so if you have a collection of matrices satisfying those conditions, we call it a coherent algebra. And the group is transitive if and only if the identity is an element of that special basis. And in that case, we say the coherent algebra is homogeneous. Now, not every coherent algebra has anything to do with groups, so they're more general. These will come up again when I talk about quantum homomorphisms and related stuff. Okay, and at that point, I will go over this a second time. Okay, so there'll be a few questions on the assignment related to this. The key properties which aren't immediately obvious is your closure into transpose and this product. Now, in this case, well, I've got to be careful. What I'm saying is if I'm dealing with the orbitals of a group, then these 2 conditions hold. And so what I propose to do is then to take this collection of 5 conditions as axioms. And the set of matrices that satisfy those axioms is what I will call a coherent algebra. Okay, and you can think of it as an algebra in 2 different ways. It's an algebra of matrices with matrix multiplication and matrix identity, or it's a vector space of matrices, which is an algebra with respect to the Schur product and contains the identity for the Schur product. So there are 2 algebra structures, which is one more than you usually get. Okay. And these things arise whenever you have a transitive permutation group. And for example, Barboy makes extensive use of these in his work on graph isomorphism, so that they're an important tool. Any questions at this point?
Yeah, just to clarify, when we're working with undirected graphs, we assume that they're simple, so no loops. But with directed graphs, we're allowing loops.
Well, in this case, except when I'm working with these coherent algebras, I'm allowing a directed graph where I've got just a bunch of vertices, some of which are loops and some of which are empty. So, and if it's transitive, then I'm in a sense I'm allowing the graph where I have within vertices with a loop on each vertex and no other arcs or edges.
Right.
Now, since that's always there, and since it's just the identity, we tend to forget about it.
Right. Okay.
The point is, if you have a graph and you're looking at the group, and a graph is simple with no loops, and then you decide for some reason to put a loop on each vertex, it does not change the group at all.
Right.
Okay, so the convention will be, so the convention is that the graph's simple, no multiple edges, and loop free. And okay, in the case of these coherent algebras, there's some, well, I haven't called them graphs yet, so I think I'm safe. But in the case of, I call them directed graphs, and I'm implicitly, if you want to look at it very carefully, I'm implicitly allowing loops, okay, on some of the orbitals.
Okay, it's just to make the coherent algebra picture work out nicely.
Yeah, I mean, I want them to sum to the all ones matrix.
Okay, that makes sense. Thank you.
And the other point is we have coherent algebras and permutation groups, and we have transitive permutation groups. And so, what's the analogous condition for coherent algebras? Or the analogous condition is that the identity is not just a sum of matrices in the current 0-1 matrices, but it is actually equal to one of the matrices in this basis. So it makes things work nicely.
All right, thank you.
Yeah, loops only cause problems when you start thinking about homomorphisms from one graph to another. If you're dealing with automorphisms, you can put loops in or leave them off. It won't cause you any real grief. I want to now going on to Cayley graphs. This is not directly related to what I just said. So we can view this as a construction of interesting graphs. So, and well, we need them sometimes. So we start with a group G and we choose a subset C of the elements of G. And then I'm going to define the Cayley digraph X, G, comma, C to be a graph, or a digraph whose vertices are the elements of G and whose arcs consist of the pairs GH such that HG inverse is in C. Now, I tend to be lazy and refer to, I'll often, when I talk about Cayley graphs, it may be that I mean a Cayley digraph. Okay, but I'm going to try to be careful for a while here. The other comment I need to make is that it matters here whether you put HG inverse or GH inverse. Okay, there's this question of whether things act on the right or the left, and so I've chosen this so it makes stuff work. So now, if the group's abelian, then the order doesn't matter. But if it's not abelian, then the order matters. And so you need to remember that we're taking HG inverse. So the way I've set it up is that the identity in G is going to be adjacent to C for all C in G, or C in script C. Well, actually, more precisely, C is an arc for all C. So I'm just saying this matters, and you need to pay attention. Well, we'll see about that. So I've defined the graph, and I've told you what the connection rule is. This set C it is usually called the connection set for the digraph. Now, some of you who know about this will think I should have added a few conditions to C, but we'll get to this now. So the first thing now is that the digraph has loops if and only if the identity element of the group is in C. In that case, there's one loop on each vertex, and as I was just saying, having one loop on each vertex does nothing to the Wilson group, so it's natural to assume in general that one is not in C. Okay, and so we're doing that. The second thing is often we want a graph and not a directed graph. And so the condition we need on C to get an undirected graph is that C is equal to C inverse, where C inverse notes the set of inverses of the elements of C. So if we had these two conditions, then our Cayley digraph is a Cayley graph. And I don't think I'll have much reason to consider Cayley digraphs. Okay, so generally we're dealing with Cayley graphs. And so we arrive at those by assuming that the identity does not belong to the connection set and the connection set's closed under inverses. Now, generally, I'm sort of assuming the group is, I'm writing the group multiplicatively. If you're working with an abelian group, then you would use, generally often use addition. And in that case, you don't want the 0 element C. Okay. Any questions at this point? So here in all its glory is a cycle on 7 vertices. The connection set is 1 and minus 1 what 7. And so you do that, and lo and behold, there's the graph. I couldn't have picked now. Okay, I could have picked a simple example. Every complete graph is a Cayley graph. You just take your set C to be all non-identity elements of the group. Okay, so every complete graph is a Cayley graph, and so the complement of the Cayley graph is a Cayley graph. Okay, so now you've got two infinite families: the complete graphs and the empty graphs. And you also see that this will work for cycles. So cycles are Cayley graphs for the cyclic group. Now a Cayley graph for the cyclic group, if I got it here, is generally called a circulant. I should say that it's not impossible for the same graph to be Cayley graph for two different groups. And so your first exercise in that sense is to show that, for example, the 4 cycle is a Cayley graph for two different groups. Okay, so the graph doesn't determine the group. The other class of graphs we actually spend a reasonable amount of time with is that a Cayley graph for the Z2 to the D is a cube-like graph. So this is just the terminology I think is due to Lovaas. So you're looking at the binary vectors of length D. And so the connection set will just be a set of a non-empty set of binary vectors. We don't need to worry about the inverse condition, because if you've got order 2, you are your own inverse. So to get a cube-like graph with those loops, you just take Z2 to the D and pick some subset of the elements that doesn't contain 0. Now, Z2 to the D is a vector space of dimension D over the field of order 2. And so we can use linear algebra rather than group theory to work with it sometimes. If you take the standard basis as your connection set, then the cube-like graph you construct will be the D cube. I mean, well, since it's easy, I can remember it. So there's the 2 cube. Okay, and so the connection set is the way I've done it is 0, 1, 1, 0. Okay, and so actually, when you construct the Cayley graph, each arc is determined by an element of the connection set. Okay, it's labeled by G or G inverse. Okay, and so in this case, since we're elementary abelian of order 2, there's no difference. So this edge corresponds to this element of the connection set. Okay, and so does this edge. You're adding 1, 0 to 0, 1 to get 1, 1. You add 1, 0 to 0, 0 to get 1, 0. So these two edges correspond to 1, 0. The other two edges correspond to 0, 1. Now, the groups you're used to working with are cyclic groups. You may well run across dihedral groups. You can show that an even cycle is a Cayley graph for the dihedral group. Now, an even cycle is a 2 regular graph. So you're going to have to pick 2 elements of the dihedral group that generate it. Okay, and it's not too hard to find them. Beyond that, of course, symmetric groups are too big, and it's hard to get a real feeling for graph by staring at pictures. But but the cuboid graphs will come up a number of times as we go on when we're talking about quantum walks. Now, the Cayley graph is its vertices are the elements of a group. And so, in fact, we get some automorphisms of the graph for free. And so I want to talk about that. And the claim is, okay, so I need to define, I want to get an automorphism G, so I've got to give you a permutation of the vertices. Now, the way I get the permutation is I pick an element, little g of the group G, and I multiply each vertex on the right by little g. Now, that is a permutation of the vertices. Okay, so that's a bijection from the vertex set to itself. Okay, and the claim is that for each little g and big G, the automorphism, the permutation rho G is an automorphism of XGC. Okay, now I've got G on the right here, and that's why I'm using rho for right. If I want on the left, I'd use lambda. So we're acting on the right. Okay, and that is an automorphism. Now if you take the action on the left, you map X to GX, that's a permutation of vertices. But if your group is not abelian, that will in general not be an automorphism. Okay, so the order matters, but as stated, well, I've got a proof here in the notes. I don't know this. Well, yeah, it is working through. If I have XY vertices next, then rho maps the pair XY to the pair XG, YG. And now we just check the adjacency condition for a Cayley graph. So we take the second vertex followed by the inverse of the first vertex, and we get this. And so the GGIs go away. And so we conclude that this is in script C, the connection set, if and only if, if and only if YX inverse is in script C. So in other words, YG and XG are adjacent if only if X and Y are adjacent. So this is not a deep result, although it's actually maybe did deep, but it's not hard to prove. Now, so this gives us, so we now have one automorphism for each element of the group G. And so particularly you see that I can, if you pick an element H of G, I can find an automorphism of the graph which maps the identity element to H. I just multiply on the right by H. So the group, not only do these maps rho G give me automorphisms, they give me a transitive group of automorphisms. And the map that takes G to rho G is an isomorphism. So the group itself is acting as a group of permutations on the vertices. And there's an extra property that the only element of the group which actually fixes some point in its action is the identity. And so this group is what we call a regular permutation group. And of course, regular is the most overused word in mathematics. But so the group, the jargon is the group acts regularly. It's transitive, and the stabilizer of a point is trivial. So we know that the order of the automorphism group of a Cayley graph on a group G is at least the number of vertices, elements of G. Okay, now it's an obvious question to ask, well, when is it actually equal to G? Well, this is one case where it fails. If you have an automorphism of the group, which maps the set C to itself, then probably some bit of notation here, then psi gives you an automorphism of the graph. It fixes the identity and permutes the vertices adjacent to the identity. Now, how can you get such an element? Well, if you have an abelian group and it contains an element of order at least 3, then the map that sends X to X inverse is a non-trivial automorphism of the graph. It fixes the set C because C is closed on an inverse because we wanted a graph. Okay, and so you get a non-trivial automorphism. So if you have a Cayley graph for an abelian group, and it's not an elementary abelian 2 group, then it has an automorphism which fixes a vertex. And so the order of the group, the order of the automorphism group is at least twice the order of the group. Okay, and so twice number of vertices of graph. So the stabilizer of vertex in the graph's got order at least 2. Now you can generalize this a bit. If you have, so if you've got a group and you can find an automorphism of the group which maps, or if the map that takes X to X inverse is an automorphism of the group, then you get an extra automorphism. Okay, and it's a non-trivial theorem that if your group is not one of those two families, and the order is I think at least 32. If the order is at least 32, then you can choose your connection set so the orbital group is just a group you started with. But that's a largest result, and it represents a lot of work. So we can construct things with Katie graphs. They're interesting because one reason is they give us graphs where we have something, a non-trivial group action, a non-trivial group acting on it, and so they have some symmetry. And we'll see if they're useful now. And this is exactly where I should stop. So any questions?